This video is an introduction to exponential functions. Let's suppose we're studying the population of some beetles in science class, and every week we're going to determine how many beetles there are in the population. So before we start the experiment, we start with 2 beetles. After the first week, we see 6 beetles. After the second week, we see 18 beetles. After the third week, we see 54, and after the fourth week, we see 162. Now on the left, the number of weeks is going up by 1 each time. There is an additive relationship. Let's see if there's also an additive relationship on the right-hand side of our table. From 2 to 6, we need to add 4. From 6 to 18, we need to add 12. From 18 to 54, we need to add 36. And from 54 to 162, we need to add 108. Clearly, there is not an additive relationship between the numbers on the right. We are not adding the same quantity each time. So perhaps instead of an additive relationship, there is a multiplicative relationship. To get from 2 to 6 with multiplication, we would have to multiply by 3. 2 times 3 is 6. 6 to get up to 18 is also times 3. 18 times 3 is 54, and 54 times 3 is 162. So now, instead of there being an additive relationship between these y values, if you wanted to think about them that way, right? The number of weeks being an x value and the number of beetles being a y value, now there is a multiplicative relationship. So before the experiment started, there were 2 beetles. After that, there were 6, which we can think of as 2 times 3. On the second week, we had 2 times 3 times 3, right? 3 times the previous week. On the third week, there were 3 times as many. So 2 times 3 times 3 times 3. And on the fourth week, there were 3 times the week before. So 2 times 3 times 3 times 3 times 3. Well, we know that there's a better way to write this. We can write these with exponential form. So I'm going to start here where there's 2 3's multiplied together. I can write this as 2 times 3 squared. And this third week I can write as 2 times 3 cubed. The fourth week I can write as 2 times 3 to the fourth. And if we go back here, look at week 1, we can write this as 2 times 3 to the first power. And in fact, before we even started, we could say that this is 2 times 3 to the 0 because remember that 3 to the 0 really equals 1, which means that 2 times 3 to the 0 equals 2. So there's a pattern developing here that I'm hoping you're noticing. Here, 0, 1, 2, 3, 4, these exponents correspond to the number of weeks. So if we wanted to say the number of beetles y equals some function, we could say that it is 2 times 3 to the x power, where x is the number of weeks since the experiment started. There were 2 beetles to begin with, and every week it's 3 times as many as there were before. Let's look at 2 relations now and determine whether or not they are exponential functions. The first thing we need to check is whether there is a common difference on the x values or between the x values. So here in our first example, there is a common difference of +1 each time. If there's a common difference on the left, we can check for a common ratio on the right. Remember that we're looking for a multiplicative relationship. Well, 1.5, okay, to get up to 3 would have to be multiplied by 2 because 1.5 is half of 3. So 1.5 times 2 gets us to 3. So 1.5 times 2 gets us to 3. 3 times 2 gets us to 6, and 6 times 2 is 12. So there is what we call a common ratio corresponding with a common difference on the left. So yes, this is an exponential function. So first, for the one on the right, we need to check to see if there is a common difference. From -1 to 1, I would add 2. From 1 to 3, I would add 2. And from 3 to 5, I would also add 2. So good. We're starting with a common difference here on the left. So we need to check for a common ratio on the right. -9 to 9, I would have to multiply by -1. From 9 to 27, I'd have to multiply by 3. And from 27 to 45, I would need to multiply by 5/3. Well, clearly there isn't a common ratio here, okay? So there is no common ratio in this case corresponding to that common difference for the x values. So no, this is not an exponential function. When we talk about exponential functions, we have a couple of rules that we need to keep in mind. Remember that example we looked at the beginning that said y equals 2 times 3 to the x. Remember that 2 here was the initial population of beetles. We had 2 beetles to start with. So this is some initial amount. And this 3 here was how we got the common ratio. Okay, that told us every week that the population grows, it grows 3 times as much. And x was our independent variable, right? That was what changed each time. It went 2 times 3 to the 1, and then the next week it was 2 times 3 squared, and then the next week it was 2 times 3 cubed. So in general, we think about exponential equations being written in the form y equals some number a, some coefficient a, times b to the x power. Okay, so a is that coefficient that tells us what the initial amount is, and b is the base to which we raise this exponent x. And there are a couple of rules here about what a and b can be in order for this to actually be an exponential function. Consider, for example, can a equal 0? If a equals 0, we have y equals 0 times b to the x. 0 times anything is 0. So y equals 0 is the equation we get. Well, y equals 0 is a horizontal line, and it's in fact the x-axis. It's not an exponential function. Therefore, we have a restriction that a cannot equal 0. Here's another question. Can a equal 1? 1 times anything simplifies to whatever you're multiplying it by. So y would just equal b to the x. And here there is still an exponential relationship. B is still being raised to an exponent, and every time x goes up, y will increase exponentially. So this is fine. A can equal 1. Let's try something else. Can b equal 0? Let's see. Y equals a times 0 to the x power. Well, if you raise 0 to any power, you get 0. So we have a times 0. And anything times 0 is 0. So again, this simplifies to y equals 0, which we discussed previously is not an exponential function. So another restriction is that b cannot equal 0. Let's see if b can equal 1. Well, 1 to any power is just 1. Think about that for a second. Okay, if we plug in 1 to the first, 1 squared, 1 cubed, all of these come out to be 1. Okay, 1 to the x power is just 1. So we have a times 1, and we get y equals a. It doesn't matter what a is. This is going to be a horizontal line rather than an exponential function. So we have another restriction that b cannot equal 1. Let's consider if b can be negative. Okay, can b be less than 0? So let's suppose that we say that b is equal to -2. Let's set up an xy table and see what happens when we plug in some basic values like -2, -1, 0, 1, and 2. I'm going to start at the bottom because these positive exponents are going to be a little bit easier to start with. -2 squared. Okay, we're saying that this is -2 to the x power. So -2 squared is +4. -2 to the first power is -2. -2 to the 0 power is 1. Anything to the 0 power is +1. -2 to the -1. Remember that a negative exponent means 1 over that base to the positive version of the exponent. So 1 over -2 to the first power is 1 over -2, which we think of as -1/2. And then -2 to the -2 is 1 over -2 squared, which is 1/4. So let's see if we can get an idea of what this graph looks like. According to our xy table, there is a point at +2, +4. That's all the way up here, 2, 4. There's a point at 1, -2, down here. There's a point at 0, 1, here. There is a point at -1, -1/2, so here, in the middle of where I've drawn my number. And there's a point at -2, +1/4, here. Notice how this graph is zigzagging back and forth between a positive number and a negative number. And that makes sense because when you raise a negative number to an even power, it becomes positive. And if you raise a negative number to an odd power, it becomes negative. Now, these are only plugging in whole number values for x. When you get to Algebra 2, you'll learn about why we can't put a fraction in the exponent here with something like -2 as the base. Okay? It is possible to get an answer for that, but it's not a real number answer, which means it's not something we can put on this graph. So actually, all of the points that we would want to plug in between these integers wouldn't yield y values that we could actually plot on this graph. So we would get undefined answers, and it flips back and forth between positive and negative all the time. The point is that plugging in a negative number as the base, the b value in an exponential function, in fact, it doesn't get us a real numbered function at all. So b cannot be less than 0. So our last restriction is that b, in fact, has to be greater than 0. Okay, not only does it have to not equal 0, it has to be greater than 0. So to summarize, an exponential function comes in the form y equals a times b to the x, where a can't equal 0, b has to be greater than 0, and it also cannot equal 1. Okay? A can't equal 0, b can't equal 1, and b has to be greater than 0. And notice that I didn't write this restriction down because writing b is greater than 0 implies that b can't equal 0.